For this video, I'll be working through question 5 of the 2018 Scholarship Physics exam. Radio, question 5. It's about capacitors and dielectrics. Describe the electrical properties required for a material to act as a dielectric. So pause, write the answer and discuss. Right, so I've said it must be an insulator, but also be polarizable in the presence of an electric field. So this question I've actually never come across before in my life. I've never actually thought about this, to be honest. I always tell my students everything is a conductor if you have enough electricity, which is kind of true. If the voltage is high enough, everything will conduct. Either that or just catch on fire. But what makes a conductor and what makes an insulator is on the outer shell of any electron, you have the excited states that the electrons can jump up to. The jump of those states, so how much they have to jump, determines whether something's an insulator or a conductor. This is like the simplified explanation anyway. So metals have a very small jump from the ground state of that outer shell electron to the next state up. So they have like a sea of electrons that can just jump up and then escape and then float around amongst the metal. Insulators, however, such as like plastic and rubber, there is a massive jump for them to overcome in order for them to be able to be free. So plastics, rubber aren't polarizable whatsoever, and they're terrific insulators. Sulfur hexafluoride gas as well, the stuff that makes your voice real deep. It's an amazing insulator. It's what they pump into high voltage power stations, and people put like scuba suits, or not scuba suits, but like gas suits on. Anyway, so a dielectric is somewhere in the middle. So glass, for example, probably not glass, probably like water. Water's an insulator. You can Google it, people putting like toasters in baths and stuff like that there. The results that come out is water doesn't conduct very well at all. However, if you put salt in it, so human sweat, stuff like that, it is a conductor. Anyway, that's enough for that one. Right, so capacitor containing a dielectric is initially charged and then disconnected from the battery. The capacitor then has its dielectric removed, as in the diagram above. Show the minimum work required to move the dielectric is that crazy formula where CF is the capacitance of the capacitor. With the dielectric removed, VF is the final potential difference, and ER or epsilon R is a dielectric constant. Sweet as. So notice, switch is open. So I've charged up and open the switch. So now our conserved quantity is charge. So I'm going to write charge is conserved, full stop, and then I'm going to write QI is equal to QF. In other words, the initial charge is equal to the final charge, and you can check that over here. CIVI, so charge initial, voltage initial, is equal to charge final, voltage final. And how the capacitances are related to each other. The initial capacitance is equal to the final capacitance times the dielectric constant. This is kind of a tricky thing to sort of get your head around. Like this here, if you could times the final capacitance by the dielectric constant, you would get your initial capacitance, because this capacitance contains the dielectric constant. So that inside this formula is the ER. And just remember, dielectric constants just scale up capacitance. So if you have a dielectric constant of 2, it just means your capacitor can hold double the original amount of charge. Yes, probably. Anyway, what do I need to do next? So change in energy is equal to, on your formula sheet, there's what is it? Is it on your formula sheet? You should probably just know it though. Where is energy? I'll see if I can find it. Yeah, half QV squared, but Q is equal to CV. So I'm going to go half CV times V, and then it ends up, it's just half CV, I should say, QV. It's CV times V, which means V squared. So you end up getting, so it's final minus initial, CV, it's going to be a half in there as well, CV squared, sweet, minus the initial, CI, should be a half in there, VI squared. Yeah, that's it. And now that is going to be equal to, I'm going to pull the half out, CFV F squared minus, and then we go Ci, and now I'm going to substitute in for Vi. I know Vi is equal to Cf Vf divided by Ci. You can just move that Ci underneath. So I'm going to have, I'm going to put brackets around it because I'm pedantic like that. Cf Vf, that's that part up there, divided by Ci, and that equals Vi, and because it's squared, sweet as. Brackets around that, and then I'm going to blow this up a little bit. Half Cf Vf squared minus Cf squared Vf squared over Ci. Same as before, brackets around that. Oof, I'll run a bit of space, and that is going to be equal to half. And what I'm going to do is I have Cf Vf squared. I'm going to do like 2 or 3 steps in this one. Yeah, because what I'm going to do is I'm going to bring this this epsilon, this dielectric constant, and this Ci is equal to these two. So if I bring them into there, that'll cancel out one of the squares. So you'll soon see. Cf oops, bracket, get rid of that brackets. Cf Vf squared outside of the brackets. Brackets here, 1, because that you times this through and you get that one there. So it's 1 minus, and we're going to have, I've pulled out the Cf Vf squared. In fact, what I'm going to do is I'm going to leave one of the Cf's in there, just so it makes sense. Cf, because I just pulled one of them out, over Ci is equal to ER Cf, epsilon R Cf, dielectric constant Cf, bada boom. And now we can cancel these two Cf's out, easy peasy. Half Cf Vf squared times, why am I putting brackets there? Brackets here. 1 minus, what do we got? 1 over E, or the dielectric constant. Now, hopefully, I don't forget to put those brackets. Half Cf Vf squared. And now this, to rearrange this, you do like the old year 10 cross multiply. So you turn this into, this here is a fraction. It's 1 divided by 1. That's a fraction. So you go dielectric constant times on that side. So you get ER, and then you go, no, this would be 1 divided by 1. You go 1 times 1. Hey, it's 1. Look at that. And then common denominator. And that is equal to the change in energy. Hey, you got the answer. Sweet. That's what we're looking for. Explain why work has to be done to remove this dielectric. So again, I'll pause, write the answer. Just go. Right, so I've said Q, I'll start with the formula. Q equals CV. Charge is conserved as it's disconnected. Because it's disconnected, there's nowhere for the electrons to go. Capacitance decreases because what have you done? You've removed your dielectric constant, so voltage increases. If this goes down, that goes up. This means work must be done for this to occur. If your voltage increases, you've got to do work. Voltage is essentially energy. It's joules per coulomb. If each coulomb has more joules than it originally had, you must need to do work for that to happen. Rightio. So we have next question. Ooh, what? If the capacitor is still connected to the battery when the dielectric is moved, as in the diagram below, the energy stored in the capacitor will decrease. What do you know? Despite this reduction in energy, work must be done to withdraw the dielectric. Explain this apparent contradiction. Right, I'll pause the video, discuss. Right, so what I've said is when connected, the conserved quantity is now voltage. Because you've got Q equals CV. As capacitance decreases, charge must decrease. The charges flow off the plates and back to the battery. Work needs to be done for this to occur. So now that it's, like, the reason why work needs to be done is these charges need to get off the plate, and the only way for them to go is to go back into the battery. And in order for that to happen, you must like overcome a potential difference. So you've got to do a little bit of work for that to happen. Right, so If the charged capacitor is held just touching the surface, the liquid of the dielectric, the dielectric will be drawn up into the capacitor. I'm assuming this is water. Pretty sure it's water. Explain why the capacitor voltage decreases when this phenomenon takes place. Again, I'll just pause and discuss. Oh, first what I'll do is I'll draw the electric field, because we have an electric field that dips down like that, and it goes from positive to negative, just like year 12 styles. Okay, yeah, I'm real messy. I'm definitely artistically challenged. So there you go, the electric field that dips into the water, which explain why the liquid is drawn up into the charged capacitor. Well, I'll answer both of them, and then I'll discuss the answers for both. Alright, so for here, why does the capacitor voltage decrease? Q equals CV, assuming it's disconnected, as the same question as before. Charge is conserved, water acts as a dielectric. Water is a higher dielectric than air. In fact, air isn't really a dielectric per se. It's pretty much a vacuum. So this increases the capacitance, thus voltage decreases, so charge remains constant, pretty much the same as before. And explain why the liquid dielectric is drawn up into the charged capacitor. At the edge of the plates, the field lines are not parallel, they're curved into the water, as you can see. The water molecules align with the electric field and get attracted up in between the plates. Yeah, I'm still not entirely sure why water ever does this. The whole like rubber, whatever you call it, if you like rub a ruler and bring it near water, it bends, and everyone says, oh, it's because water's polar, or water can be, you know, this, that, and the next thing. Veritasium did a video on it that sort of explained it, but if you follow Bruce Yearney's YouTube channel, Yearney, I don't know how to say it, it's a homemade science. He does it with like everything, sand, he does it with oobleck, he does it with lots and lots and lots of different things, so I'm completely puzzled as to why that is the case, and maybe there's some person that's published a paper as to why that is the case. Maybe they're all sort of insulators but not entirely insulators, and that's why it works, that's why they're attracted, because the molecules can then align electric fields and then get attracted. But yeah, anyway, that's it.